guys like the actual.
You get to it. Okay, so motor,
Oh,
you ready? Oh, we're all gonna wait for Flippy?
Yeah.
Yep.
Yeah. There's two.
Okay, so, we talked about a lot of different types of motors, right? This one here is a blower motor. It's in housing and everything.
Or a squirrel cage.
Um,
They don't know the terminology.
Why? Because it looks like a squirrel.
This is a typical 3-speed motor.
3-speed?
How do you know?
How can you identify it?
It's got 3 wires.
Hmm?
Oh,
wires?
the wires.
Wait, really? Wires?
Yeah.
Okay, and we have here's another PSC, this is a little PSC motor. Someone came off my room, and this one here is the ECM motor. This is the new one.
That looks pretty dope.
Looks like a
Pretty dope.
flux capacitor.
Pretty cool, sorry. Looks like a space.
Okay, now this one is a shaded pole. I'm gonna pass this around, and I want you to identify the shaded pole. Check it out, Dave. Can you see it? Can you see it? Can you see it?
See what?
Can you see it?
Shade pole.
The shaded pole. You see it on there? You're lost, huh?
Yeah,
You don't see it?
I am definitely lost.
Right there.
Oh,
It's copper. I know it's painted.
yeah, it's paint. See, okay.
Painted copper. Okay. All right, so motors are a big part of everything that we do. Now, I'm gonna make a statement that motors never die a natural death. Motors are murdered.
Can you elaborate, please?
They're murdered. That's why they go bad. They
Right.
are murdered.
How are they murdered? Like, cause they weren't taken care of?
By getting overloaded by user error.
All that.
So
If the
technically
motor-
not getting.
If this motor
Uh huh.
is supplied the proper voltage, and it has the correct load on it,
Continue.
and it's allowed to stay running, it has the proper cooling, then that motor will run indefinitely. Okay, motors are murdered because they're overloaded or underloaded. Or they got the wrong voltage on them, or the capacitor goes bad. A lot of things can happen to a motor. They can overheat. If they overheat, they're not cooled properly. Okay? If they're constantly turned on and off, that will kill the motor. So turning them on and off is bad for them too. But we need motors, and we use motors, the way we use them, that's just what happens. We have to turn them off and on. That's like light bulbs, right?
So if you never use it, it'll last forever.
And logical, yes.
Yeah, like this one's lasted a long time. We never use it.
Has it been used or is it new?
Yeah.
Never been used.
Never been used. This one has.
Slightly.
So the ECM motor, I'll pass this around. This is the one that you'll be looking at and troubleshooting. Okay. Now the standard motor. Remember I talked to you about that, counting the poles? If you look down in this motor, you can actually see the poles in there, and they're coils of wire. So each pole has a large wire and a small wire. Okay, so you're gonna check it out?
I'm just checking.
So you can actually count those poles. See them? That's pretty slick, huh? Okay, so, right here, this is what we learned about, this is the current relay. Current relay. You can see how thick that wire is, that wire goes in series with the run winding.
Which one would be the poles?
Huh?
These right here, straight in, right here?
The loops of wire. See the wire in there? There's ones on the inside and there's ones on the outside. You can tell the different size of wires. You can tell which one's a run winding, which one's a start winding. Because the run winding has what? Less turns and it's thicker wire.
Okay.
You know that because it's drawn up here. Less turns, thicker wire. Start winding has thinner wire and has more turns. Okay, that's gonna be important because we're gonna do another project in a couple days about where we're gonna have to ohm out compressors. Compressors are interesting because they're motors. They're split phase motors. And yet, on the compressors themselves, they're gonna have 3 terminals sticking out of the compressors that look like this. 1, 2, 3. So in order to identify those, you're gonna have to use your ohm meter to figure out which winding is which. Okay?
Yes.
Again, that could be something that they're gonna ask you on an interview. So you're gonna have to know this stuff. It's like little pins that look like this, kind of. We'll get into that in a, maybe more, maybe. Okay, so here is the PTC, or the Spock's father, the Siroc. This is replacing the potential relay. See that?
Oh. You said there's one that has a shade on it.
DCM.
Where's the shade on it?
Okay. That copper band right there?
This one?
That's the copper band. It's black because the paint is black, but it's copper. That copper actually disturbs the magnetic field.
Disturbs my negative field.
Yeah.
Like
Disturbs.
Oh.
Yeah.
So would
It
it?
causes it to act weird.
Um,
It doesn't, it's not a pure, because copper is not magnetic. It also affects magnetic field inversely.
Never knew that.
Yeah.
So it's a good source of current, but not for magnetic purposes.
Right, and they utilize that in the shaded pole motor because they know it doesn't affect the magnetic field. It doesn't energize the magnetic field as fast as it does with the unshaded portion.
Wow.
Really weird. Copper and magnets are really weird.
Yeah, I could clearly see now.
Anybody know what this is?
The rotor.
How'd you know that?
Looks like a rotor.
Cause that's the thing, it rotates.
The rotor. This is a squirrel cage rotor.
Oh, use the rotor.
Wow.
Ooh, spinner.
You done with that?
And it's a spindle.
Okay,
That's a new one, right?
so
Gonna look at.
here are some of the issues that we've had with motors. You guys focus now?
Screw Eric.
No.
Ready?
Steve, what's this one?
I knew I shouldn't have done that. I knew I should have pass those out.
Steve,
Pass which one's out?
what is that?
That's a thermistor. PTC device.
It's been for me. 3 days.
Question, I got the gist of it.
Okay. We also have a three-phase motor in the back there.
There's
Also-
more than 3 wires here.
Okay,
Yeah.
so when we're talking about motors, we have an awful lot of information that we have to deal with when we're talking about motors, especially when we're gonna replace a motor. We have to get all the information off of that motor, because there's so many motors out there that you could end up burning the motor up once you put it in, okay? So you're gonna have to look at them real careful, and you're gonna have to get all the information off of them. We're gonna spend the entire week talking about motors, specifications, and how to replace them, okay? You got that so far? Okay, so motors, like I said before, they are not, they're not indestructible. They will go bad if you wire them up bad. We know from our schematic diagrams that this common is gonna go where? Where? Where's it hooked to? Where's it hooked to? Where's it hooked to? You guys don't remember? Go get the handout.
L2.
Right there in front of you.
Oh, one,
L1 and L2, right?
yeah.
Right? Just like that. Okay. Are we good? We're good so far?
Yeah.
Partially good.
This is gonna require maybe a switch,
Maybe.
maybe.
Maybe, depends.
We'll put a set of contacts in there and that's right there, right? So that could be a centrifugal switch, we call it a centrifugal switch. How's that?
CS.
Okay? So in this case, the split phase motor, this one happens to be, single speed. So here's the problem that we had, and, one of the suppliers goes around and does this, seminar, Motor Matters, called Motor Matters. And he can do it, we did it a lot at the other place where I taught. Every 3 months, he'd come in and he'd do this Motor Matters seminar for all the classes. And, he's pretty thorough, he's the owner of one of the local supply houses here. Name is Danny Collenbeck. He owns Johnstone Supply in Fresno and in Salinas. But the way he would do his seminar, he would say, look, if we got a motor, like that one, he goes, I'll sell you a motor, if you want a motor, I'll sell you this motor, okay? If you burn this motor out, you'll bring it back and I'll replace that motor. But if you burn the second one out, then I'm gonna ask you, what are you doing with it? How are you hooking up? What are you doing? He says, because I've replaced so many motors from students that wanna work on their own stuff, that for one, they don't know how to hook them up. They don't know what the wires mean. They're not getting the right motor for the job. They're putting in the wrong horsepower motor, wrong voltage. He says, that's why I created this seminar, and that's why I go around to the local schools and I give this seminar on all these motors. He'd bring in all the motors that he have and he'd explain it. And it could be, his seminar he can go either 1 hour, he can go 2 hours, or he can go 4 hours. He goes, which one do you want me to do? So we tell him which one, he'd go through it, and I sat through a number of those seminars. And what he did is he explained the motors, he's not afraid to replace a motor if it's bad, but he also wants people to learn the things about the motors that not normally that are not normally taught in school, right? One of the problems that he had was sometimes they'll use an 825 RPM motor for condenser. And what happens is with that 825 RPM, they started doing that because that motor spins at a slower speed. Clear my throat here. It spins at a slower speed. It moves the same amount of air, but it's a lot quieter. This was particularly useful when they were putting condensing units outside in the backyard on the ground, especially having that unit outside the bedroom window. They didn't want that thing. The older units were really loud, and they would normally use a 1075 motor to push the air. So they went to the 850 motors to keep the noise down, the air noise and the motor noise. But the problem was those 850 RPM motors were pretty expensive at the time. When you can get one of these for maybe 28 bucks, the 875 motors were running about 90 bucks. So technicians in their infinite wisdom that they have in the trade, they look at the price and they go, nah, I can do this better. I can get it off, yeah. So what they're doing is they're putting a multi-speed motor in place of that condenser motor, right? So they figure, oh, I'm gonna put that motor down on low speed, and that'll get it going, that'll work it. Okay, so what determines the motor speed?
The number of poles. Yeah.
The number of poles, right? Okay, this particular motor, if this is the replacement he's gonna put on there, this is a 1075 motor. I don't know if you can still read it on there, it's all piped on. This is a 1075, this is 1075 RPM, which means it's a 6-pole motor. Okay, so what speed does it run on low speed? What speed?
How much was low?
Huh?
How much was
1075.
1075?
It's a 1075 on
Right here, your suggestion.
I don't know.
there. You know? Any guess?
300.
Low.
Huh?
I don't know.
On the low,
On low, yeah.
like 300. Let's say 400.
400.
350.
Okay. What if I told you the low speed is gonna turn 1075?
1075. 1075.
Because what determines the speed of this motor?
The amount
What?
of the poles.
The number of poles, right? We didn't change the number of poles, so this motor's gonna run 1075. High speed
Oh,
Low
high
speed
speed makes it.
and medium speed. It's gonna run 1075. That's what it's made to do. Well, wait, well, why is there 3 speeds? This one has 3 speeds. Why is there 3 speeds? Very good question. Remember the drawing on the PowerPoint that looked like this? Where you had the start winding up here? And then you had a run winding down here?
Mm-hmm. Okay, yeah.
Went like this, right? And you had a little switch in there, I guess.
Oh, yeah. Now on the other
And then you had
side.
the run winding like this. Remember that thing? Then you had all these different speeds. Right?
Oh, okay, yeah.
L1 and then L2
Mhm.
was either one, right? You can go either one. Pick your speed. Pick your speed. What do you want to run it at, right? Remember that?
Mm-hmm.
Okay. This is what happens with the motor. We didn't change the poles. We actually made that run winding longer, way longer. Mucho longer. Okay, so on a multi-speed motor, basically what makes it go at a different speed is the load. So there's a load on this motor at low speed where it is trying to get to 1075, but it just doesn't quite get it. It just continually it just constantly trying to get up to speed, but it never does. That's how the speeds are created on a multi-speed motor. As you can see what that does to a motor? It's just constantly trying to get up to its design speed, and it just never quite gets there.
Pretty depressing.
Yeah, pretty sad.
Huh?
Pretty sad.
Yeah. The way they get around that is they have that big old long winding. So the motor doesn't get hot, so it just runs at a slower speed because it doesn't have the power to get up to that speed, ever. So, the guy that replaced this motor and puts it on low speed, the motor burns out the following day. Because he matched it up, it's quarter horse. He got another quarter horse, and he put a multi-speed motor in there and wired it on low speed. That motor is trying to do the work that the old motor did, right? And it can't do it. It cannot do it. Because what happened is that slower motor, the pitch on that blade is so much that it's spinning slower, but it's still pulling the same amount of air out. It's grabbing the same amount of air and pushing it out, right? So you put a 1075 motor, which is gonna try and get 1075, and you spin that thing and it starts to go faster, it's pushing way more air than it's designed to. So you've got a heavier load on it. So they figured out that if that was a quarter, if it was a quarter horse, I'll write that up here, quarter horse. In order to overcome that load, you'd need a bigger motor, right? And then some people, oh, well, just put a third horse in there. Well, that's not gonna work either, that's gonna burn up too. So in order to figure out, and how they figured it out, in order to get this quarter horsepower replacement and get a bigger motor, you're gonna have to go with a 1 1/4
1 1/4.
horsepower.
Wow.
So that'll do the same work and not burn out the motor. That's
Okay.
gonna push way more air than it's designed, that unit's designed to push, or pull through the condenser. But it's gonna keep the motor from burning out. Okay, by knowing that, 1 1/4 horsepower, now you've got a bigger motor. Now you got a shaft that's bigger, so your fan blade's not gonna fit on this motor. You're probably gonna be bigger around, so however you're mounting this is not gonna fit. So you can't use it. You can't use that big of a motor because it's just physically impossible to fit in there. Okay, so by the time it's all said and done, the guy needs to pay the $90 and get the correct motor and put it in there. Okay, so doing that is not feasible. It's not physically gonna work. Putting on a multi-speed motor is not gonna work because that motor's gonna try and turn at that design speed, right? So you're gonna need an 8-pole motor to replace an 8-pole motor. Okay, you can't replace the poles if you're not sure what the speed is. You can't read the tag on it, then you probably need to take it apart and count those poles, find out what speed that is. Don't assume that it's a 1075, which is the most common motor in our industry, it's a 1075. Don't assume that it's a 1075. Don't do what I did. Okay?
So the person in that story was you?
No, that's.
Steve knew better.
another- Yeah, I did replace one that was the wrong one. I put a 1075 and priced an 850. But that was because I couldn't read the label. I couldn't read the label on there. I didn't know what it was. It was a guy that, it was next door to our shop where I was working. And I went up there, and it's an old unit, probably 50 years old. I never even thought that they had 850 motors back then. I looked at I couldn't read it, so I looked at the data plate and it said 3rd horsepower, so I just went and got a 3rd horsepower, like this one. Except it was enclosed. And the next day I was over there and the thing was just really hot. I mean, I couldn't even touch it, it was hot. It had already shut off, the motor had quit. So I started looking on the data plate, and down at the bottom of the data plate, it said condenser motor was 850 RPM. And I went, oh God. So I went down and I told my boss, I said, man, that's the wrong motor, it's an 850. He goes, what size was it? I said, it's a 3rd. He goes, just put a half in there. And I said, that's not gonna work, because I'd already been to the seminars. I already know it's not gonna work. What do you mean it's not gonna work? It's just not gonna work. It's, you know, in order to overcome that, I'm gonna need a horse and a half. And that ain't gonna fit in there. He goes, well, how do you figure that? I said, well, I've been to enough motors. That's not what you do. So, I said, I don't wanna have to go buy another motor. The motor still worked. It just got hot and shut off. I don't wanna have to buy another motor. This is ridiculous. It's our neighbor. We're not marking anything up. So what I did, check this out. What I did is I measured the opening where the fan was and took the pitch on the fan, because I had a pitch gauge. And I measured the pitch and the diameter and the shaft size, because obviously the shaft size was 1/2 inch. And I went down to RSV, which is local, right around the corner there. And I said, the unit was a 3-ton. And I know that a 3-ton has to move 800 CFM per ton across the condenser. So I said, I need a fan blade that I'm gonna put on a 3rd horsepower. And I said 2400 CFM, that's what I need. FM. And here's how this is, it's 22 inches, 1/2 inch shaft. That's what I need to do. This is 3rd horsepower. 1/3 horsepower. And they opened up the books. When they opened up the books, they found family that would do that. I said, that's the one I want. And he goes, I happen to have one in stock. And I said, great.
Perfect.
So I bought the fan blade, it was like 26 bucks or whatever. Replaced the fan blade, never had a problem with it. But I knew what it was and I knew what it needed. And I could go and ask for a fan blade with those specifications. And they would match one up for me in the fan book. Okay? What does that mean?
Static. I just said like that. I just like,
Uh-huh.
come on, Steve.
Oh,
Gotta fix it. Alright.
gotta fix it, huh? Okay, so we're talking about multi-speed and multi, when you have different poles, you're gonna have you just don't wanna open your mouth, huh?
Yeah,
I don't blame you.
I'm paying attention.
So a 6-pole motor is gonna turn how many RPM?
Trans 45. 45?
You guys didn't write that down, huh? It was up on the board.
What?
1075 RPM.
Huh?
1075 RPM.
1075, that's a common speed for the 1200, in the real world. In a perfect world, it'd be 1200, but we don't live in a perfect world, so it's gonna be, and that's the difference of those two numbers, or what? What's it called?
25.
Huh?
125.
What's it called?
Slip.
Slip?
Yeah.
Slip? This could be a test question.
I wouldn't doubt it. It's gonna be a test question.
Okay, so this is another thing we learned in the seminar. Was if you got a bad motor, right? You're out there on a service call. He goes, chances are, there's a good chance that the capacitor's bad.
Okay.
They said, go down to your truck and get a new capacitor, and put a new capacitor on there, see if it works. You're gonna have to go down to your truck anyway, if you're gonna replace the motor, so if you got the motor in stock, you know. So you might as well just get the capacitor, then you got the capacitor already up there anyway, you gotta replace the motor, right? Make sense? So you put a new capacitor on it, and you check it out, and you start it up, and it works fine. Now that's happened a lot more than it used to happen before. So now, with capacitors, because they go out all the time, that's why we went through that exercise of checking how far they're off, if they're within tolerance of the capacitor itself. And yes, you'll be able to read them because nobody touches them when you're in the unit, right? So capacitors are a big thing with motors. I mean, there's been a number of calls that I've gotten lately. Say my air conditioner's not running, and I said, well, I got just a guy for you. Here's his number. And it says probably just a capacitor, and that's what it is. I've done a change capacitor, the motor still works fine. I always put a disclaimer in there though. I said, I don't know how long it's run with the bad capacitor. I don't know if there's any internal damage done into that motor, so I can't guarantee that motor's gonna run. I don't know how long it's gonna run. It could run another 5 years, could run another 5 minutes, I don't know. It's like trying to figure out when the light bulb's gonna burn out. So, by changing the capacitor, you get them up and going, and that's what you need to do. So, as long as it works when you're done, as long as you tell them, I don't know if there's any damage been done in there, we can check it, I can ohm it out, I can check and see if it's okay, but I still can't guarantee that it's gonna last, because it could hurt the motor by running it with that capacitor. Okay? Another thing, I think I told you this before, another thing that I've done, this is a shortcut. We all know what this does, right?
Mm-hmm.
We all know that, right? We went through all this, right? You remember, this corrects the phase angle, right? The phase is out of phase on an induction load, which is a motor. Well, this corrects that phase angle. This puts us back in phase. It trues up the power, right? Okay, and I told you this before, I said when the customer asks me, when I say I replace this, and they say, what is that? And I say, it's a capacitor. They always ask me, oh, what does that do? Okay, the first time they asked me, I tried to explain what it took me an hour to explain about the phase angle. And I tried to explain that really fast and it didn't really work. So I learned from that. I just said, I learned that when they ask me, oh, what does that do? I just say, this corrects the phase angle. And they never ask me, what does that mean or nothing. They
Never
just-
ask
they
what's
just
the
go,
phase
okay.
angle?
Okay, yeah, they don't ask, what is
Right,
phase
because it sounds
angle?
like a big word, and like, okay.
Because that's what it does. It corrects the phase angle. That way I don't have to get into a long explanation on what the capacitor actually does. I can get going on my next call. So, make sense?
Makes
Someone to
sense.
Google it.
What?
Someone Google it.
Someone to Google it.
Yeah. And they might get about 10 different explanations.
Yeah. If you don't.
And then they could pick the
And
one
none
they
of them
like.
will be right,
Mhm.
okay? So, here's what we're gonna do. If we have this motor, let me eradicate some of this stuff. If we have this motor, and we have, it's looking at this, so check this out. You guys paying attention?
No.
Run. You're not, well, pay attention. Pay attention. Let me grab this compressor back there.
Don't do it.
Is it run? Okay. This is actually gonna be a lab. We won't have time to do it today, but maybe we'll get to it.
Maybe tomorrow.
Maybe.
Eventually.
Okay.
Eventually.
This compressor, if you look at the top of it, see that?
Yeah.
See up on the top there, right there?
Okay.
Those little pins right there?
Yeah.
Okay. This is a Japanese capacitor. So they don't identify the terminals like we identify ours, but it's still the same thing. It's just identified differently. So on this, I like using this one because you can't tell which one of these terminals is which,
Correct.
right? So what we're gonna do is we know that this is what's inside there.
Correct.
Right?
Mm-hmm.
We know if we take an ohm meter and we measure the resistance from here to here with our ohm meter, we're gonna read a certain amount of resistance across that run winding, right? Okay? And we're also gonna do this up here, and we're gonna measure that start winding, right? And we're gonna measure another resistance, right? Another value. And then we're gonna come back here and we're gonna measure this right here. So if we know what we're doing, this is ohms, and we know where we're measuring, we can determine which terminal is which. Okay, you wanna see how it's done? See how it's done?
Mm-hmm.
Okay, so if I give you some numbers, so suppose this is, we're gonna read 3 ohms on here. Okay?
Okay.
I'm throwing numbers up there.
Okay.
Just throwing numbers, right? Okay. And then up here on the start winding, because it's a longer winding and it's smaller wire, it's gonna have a bigger resistance. So maybe it's 7 ohms.
Okay.
These are ohms, right?
Correct.
7 ohms. Okay, so it stands to reason that if we measure from here to here, what are we actually reading?
The.
What?
10 ohms,
Why?
because
Cause they're, yeah,
Oh, yeah, that makes.
Because you're reading this one and this one, right? That stands to reason, right?
Okay.
Okay, so you could have 10 ohms here. Right?
Correct. Okay.
So by taking these 3 readings, you should be able to determine common start and run on any compressor that's not marked. Why is it important that we identify the terminals?
So we don't burn it out.
How would we burn it out?
Put your start on the common, and that's not gonna be very,
Yeah.
your pressure won't.
We wire it all backwards. Right? Okay, we know that L1 and L2 is supposed to go together. Right? To start and run. We know that. The start winding has to be hooked into somewhere where it's gonna turn itself off, let's say. We're gonna have to have a switch in the circuit somewhere where that start winding gets taken out of the circuit. Okay? You get that? You understand it? Good. I'm glad you understand. You don't look like you understand it.
Yeah, just real tired.
Okay. So, we got all that, and we got this I know there's a whole bunch more stuff that I need to cover, but I can't remember all of it. Covered that, covered the speed of the motor. It's important to remember that the speed of the motor is determined by
Number of poles.
number of poles. It's actually a Jeopardy question.
Ooh.
We're doing Jeopardy again?
Yeah.
Oh, Kahoot, it is better.
Kahoot's better.
I don't know, I like Jeopardy this one.
Jeopardy's pretty,
You like this,
pretty.
you like the
I'm
aggression?
tired of Kahoot. Come on, man.
Yeah, man.
Jeopardy doesn't have music.
Yeah.
That's that one song.
Jeopardy song.
And it's important to know that
It was close.
if we talk about some of this stuff, then we're gonna talk about the start winding and the run winding and the common and start and run terminals. Okay, this is also, let me just throw this out here. On this, which winding has the highest resistance? What?
The highest resistance,
Yeah,
the start,
start winding has the highest resistance. What's the highest reading you're gonna read off of this?
10.
10. So the start winding resistance is 7, but the highest reading you're gonna read on this is
10 ohms.
10.
Start to run.
Yeah, start to.
Okay? So it's important to realize that when you're checking these, you're checking all 3 terminals with your meter. This is how I do it. How I do it, how I explained it. I mean, there's technicians out there that still can't figure this out. But you guys are gonna be better than that.
Hopefully.
In theory.
Not hopefully.
Not hopefully.
I'll be like, you know who trained me?
It's
Steve.
simple. It's simple. You're gonna take your meter and you're gonna go that, and you're gonna look at your meter and you look at all 3 of the readings. The highest reading you got, the highest one that you have, check it out, the highest one, the one you're not touching is the common. That's the one you're not touching. You're reading the highest one, that's the common. So you identified one. You identify the one, and now you know that the lowest reading is gonna be the run, and the highest reading
It's gonna be the
from
start.
common to start is gonna be. So once you determine that's common, then you take your meter and you put it on common, and you check here, and then you check here. And the highest reading is gonna be your start, and then the lowest reading is gonna be the run. Right? That's the simplest way I can explain it. There's actually a book somewhere, I read that in too.
That makes very logical sense.
So when we do that, we got a
I
bunch
guess
of
so.
compressors out in the lab, and I'll give you a little sheet, and then you can check them with your meter, that's part of one of our lab. But it's not a lab day.
We did our lab in the very beginning.
Thank goodness I didn't bring my tools.
Huh?
We did our lab in the very beginning.
You're gonna what?
We did our lab in the very beginning, when we got here.
You did?
Yeah.
Yeah, the broom lab.
Yeah, the cleaning lab.
Yeah, we swept.
Kept our work area clean.
Yeah.
Not everybody. Not everybody.
Oh, you got a 0 for that lab.
Yeah. You got 1, 2,
You didn't contribute.
2 that got late.
Yeah. Yeah. Never mind.
Oh, sorry.
Okay, so, that's all I'm gonna talk about as far as the motors. We happy about that?
Yeah.
Okay. Good. I'm not gonna talk anymore. What do you want with that?